Hello students, today we will understand the dynamics of rotational motion about a fixed axis. We have already understood the rotational analog of various physical quantities with respect to the physical quantities in linear motion. As we know, in case of linear motion, work done is given by force multiply displacement. But in rotational motion, it is about a fixed axis and it is given by the product of torque multiply angular displacement. As we know, torque is the rotational analog of force and angular displacement is the rotational analog of displacement. So before we begin, let us understand one thing. Since the axis is fixed, so only those components of torque which are along the direction of fixed axis need to be considered here, because only these components can cause body to rotate about that axis. The component of the torque perpendicular to the axis of rotation will tend to turn the axis from its position in the direction of that perpendicular force component. That perpendicular component. So the perpendicular component of the torques we will not take into account. Only we will do the calculation based upon torques on a rigid body. So here two assumptions we are considering. The first, we will consider only those forces that lie in the plane perpendicular to the axis of rotation. Hence, we will not consider the force parallel to the axis of rotation. And second assumption we are taking here, we will consider only those components of position vector which are perpendicular to the axis. Components of position vectors along the axis will result in the torque perpendicular to the axis, which we are not considering here. Now we have to discuss, as in linear motion, work done is given by product of force and the displacement. Now here, in case of rotational motion of the body, the work done by a torque will what? Let us discuss. Work done by a torque. See in the figure, what has been given here? A cross section of rigid body rotating about a fixed axis, that is the z axis, perpendicular to plane of the page, and the direction of rotation has shown anti-clockwise. As we will consider here the forces which are lying in the plane of the rotation of the body. Let F1 be a force acting on a particle of body at point P1. The line of action of the force is perpendicular to the axis of rotation and in xy plane. The particle at P1 P1 point, describe a circular path of radius small r, small r1, that has been shown in the figure as the distance Cp1. In time delta t, particle reaches to position P1 dash. So the distance covered by particle along the circumference of circle of radius r1 is ds1 is equals to r1 d theta, and direction of displacement along tangent to circular path at point P1. As we know, d theta is the angular displacement of the particle. So work done by the force on the particle in delta t time dw1 is equals to the scalar product of f and ds1, that is equals to f ds cos d theta, sorry, cos phi 1, cos phi 1, where phi 1 is the angle between tangent to the circumference at point P1 and the line of action of the force, means phi 1 is the angle between force and the displacement. So here phi 1 is angle between f ds1. Since phi 1 is equals to 90 degree minus d theta, since phi 1 is equals to 90 degree minus alpha 1 as shown in the figure. So we can put the value phi 1 in terms of alpha 1 here. So work done is equals to f ds cos 90 degree minus alpha 1 equals to f ds sin alpha 1. By placing the value of ds in terms of d theta, the term work done becomes f multiply r d theta sin alpha 1, where alpha 1 is angle between f1 and position vector of particle at P1. The torque due to F1 about the origin torque equals to position vector OP1 multiply F1, the vector product of two terms, where OP1 is the vector addition of OC, where OP1 is the vector sum of OC and OP1. So effective torque due to force F1 will be tau equals to Cp multiply F1, or magnitude of torque tau is equals to R1 F1 sin alpha, and its direction along axis of rotation. So work done will be here equals to tau 1 d theta, where tau 1 is the tau. Similarly, if there are more than one forces acting on the body, all the work done due to different torques will be added. So, if number of forces are acting on the body, the total work done dW will be equals to tau 1 plus tau 2 plus tau 3 and so on multiply by d theta, because the angular displacement of all the particles is same in the same time interval. Finally, which can be further rewritten as tau d theta, where tau equals to tau 1 plus tau 2 plus tau 3 and so on. On dividing both sides by dt, we get P equals to dW upon dt equals to tau d theta upon dt, which can be further written as P tau omega, the angular velocity, and P is the power. So this is the instantaneous power. As we know, in the linear motion, the instantaneous power will be given by force and velocity product. Similarly here, in the rotational motion, the instantaneous rotational power is given by tau multiplied by angular velocity. Since in the perfectly rigid body, there is no internal motion, the work done by external forces is not dissipated, and it increases the kinetic energy of the body. The power we have derived in terms of torque and angular velocity. So the rate at which the kinetic energy increases can be given by the rate of increasing of kinetic energy of rotating body, that will be given by d by dt of half I omega square will be equals to I omega d omega by dt. As we know, d omega by dt is the angular acceleration. So we can further write this equation I omega alpha. By work energy theorem, the work done is equals to the change in its kinetic energy. So rate of the work done will be equals to rate of change of kinetic energy. Rate of work done is equals to rate of change in kinetic energy. So we can equate here dp by dt is equals to, so we can write here dw by dt is equals to d by dt of I half I omega square, the kinetic energy, or it will give us the power equals to I omega alpha, or since the power is given by torque omega, I omega alpha, and finally it gives the torque is equals to I alpha. The relation between torque and angular acceleration. I is the moment of inertia of the body, which is analogous to F equals to ma as a linear motion. So as the force produces acceleration in linear motion of a particle or body, torque produces angular acceleration in a body. Angular acceleration is directly proportional to applied torque and inversely proportional to the moment of inertia of the body. And it can be called Newton's second law for the rotation about a fixed axis. So that's all for today. We will do some relevant numerical based upon work done by torque. Till then, good day.